Okay. All right. Without any further ado, I'd like to introduce our speaker. It's Jan Dell'Antonio. He's a member of Skyscrapers and also a professor at Brown University. And he's going to talk to us tonight about the latest, greatest telescope, the Vera Rubin Observatory.
Can you hear me okay? Or am I too loud? Not too loud. Okay. So I'm going to begin this talk with two quick disclaimers. One is I really dislike formal talks. So interrupt me at any time. Raise your hand. We'll pause because there'll be, the questions you ask are often the most interesting ways to talk. The second is with an apology. So the Rubin Observatory is actually operational. It is taking wonderful images that are embargoed. Means tonight I will not show you any images from the telescope. I'll show you plenty of images of the telescope. But until June 23rd, I'm not allowed to show anything that's hitting the focal plane that's from the sky.
Is that due to the tariffs?
It is not the tariffs. It's basically a PR move by the observatory. They want to hog the attention. And in fact, they want to have activities on the 23rd celebrating the new observatory. And one of the things they've suggested, which we'll bring up at the end, is that astronomy clubs should organize a viewing party for the unveiling. The images are very nice. That much I will tell you. So I'm going to tell you about the Vera Rubin Observatory. This is a picture of the Vera Rubin Observatory. For many, many years, I would show cartoon diagrams of the Vera Rubin Observatory, but this is an actual photograph. The Vera Rubin Observatory technically has two telescopes. You notice there's a 1.8 meter telescope sitting next to it. The 1.8 meter is designed to do spectroscopy. It's basically a telescope that is serving as a calibration telescope to the big telescope. Each night it will look at stars to measure the atmospheric transparency. But most of the time I'll talk about the big telescope. So I'll tell you a little bit about the history of the telescope, its involvement, and what it's doing. And so I'll start with a bit of history on why it's called the Vera Rubin Observatory. Vera Rubin was an American astronomer. Her great contribution throughout the 1960s and 1970s and continuing in the 80s was the discovery of the flat rotation curves of galaxies. So she was the one who discovered this piece of the puzzle, which was a strong hint on the existence of this unseen thing called dark matter. I actually met Vera only once. During my graduate studies, I was actually writing a paper involving rotation curves, trying to measure, estimate, or come up with a better way of estimating the rotation velocities from the radio data. And so Vera Rubin came by to visit my advisor, and I spent a half hour talking to her. She suggested a paper that she and Ford and Tonnard had published in 1981. And based on that work, in fact, based on the curves on the left, which come from her work, I did some simulations in chapter 3 of my thesis, in which I thank Vera Rubin for her work. The observatory itself was born in, depending on who you talk to, either 1996 or 1998. But there was a big meeting in Aspen in 1988. This was an evidence that the Sloan Digital Sky Survey had just started operation. And because of its design, it was known. So for those of you who don't know, the Sloan Digital Sky Survey mapped the northern sky using a telescope which operates by a drift technique. So basically, instead of moving the telescope and pointing at objects, you would keep the telescope fixed and let the sky move across the telescope. And then you read out the detector at exactly the same speed as the sky collects. What that meant is you only had the time it took the charge to go from one end of the detector to the other to expose, which is about 90 seconds. It's a 2 meter telescope, 90 seconds. You can do a lot of things with a 2 meter telescope. And Sloan has done fantastic things. But we knew we could do better. And so at that meeting, 2 missions were proposed, which ultimately turned into projects. One side, led by the University of Hawaii, decided that they wanted to build many small telescopes and combine and map the sky using many small telescopes. And this became the Pan-STARRS telescope in the Pan-STARRS survey. It turns out they never got enough money. One of the things that wasn't appreciated at the time is that the camera is about as expensive as the telescope. And so if you build many small telescopes, you need to build many big cameras. So in the end, only 2 telescopes were ever built. On the other hand, the Pan-STARRS survey did do about a factor of 5 better than Sloan, and its data was published in 2019. So it is a very useful project. The other project, which turned into the Rubin Observatory, was the idea to build one big telescope and make it, which made it expensive and slow, but became the Rubin Observatory. So it was named in honor of Vera Rubin because one of the things the telescope is designed to do is to map out the dark matter in the universe. So the paper in 1998, the meeting resulted in a 1999 proposal for the dark matter telescope. This is what it was originally called. I helped write the science driver of this. And you'll notice that on the left, I put from that same article a diagram of the design of the telescope. And it's amazing, in 26 years, the overall design hasn't changed drastically. The next 10 years were spent trying desperately to acquire money and a lot of schmoozing of rich people. You'll notice that the observatory is called the Vera Rubin Observatory. The big telescope is called the Charles Simonyi telescope because Charles Simonyi is a billionaire. And money to construct the mirror. The mirror is what makes the observatory so fantastic. It is an 8.54 meter mirror, but really it's 2 mirrors with 2 different curvatures, one inside the other. So inside the 8.4 meter, there's a 5 meter tertiary mirror, part of the same piece of glass, but with a different set of curvature. You can sort of see it in this diagram during the polishing. Here's the 5 meter internal, the 6.5 meter ring of light. And it's their outer ring of light that is the primary mirror that's actually collecting. The mirror is designed in the University of Arizona's Mirror Lab. This is as big a mirror as you can make, single mirror. It's built in a spinning oven, because if you spin an oven, you can get the right parabolic shape. They had to spin it multiple times because you need 2 different parabolic shapes. And then it's built in a honeycomb structure, so the back of it is empty, and that allows it to be much, much lighter. It's already immensely heavy, but it's not as heavy as it would be as a solid.
How would they slump the middle of it differently after the outer ring was bigger?
So they filled the inner part with the material that they used the honeycomb for. So there was no glass in the interior thing.
Okay.
They cooled it, and then they heated just the interior part.
Wow.
Yeah, it's a messy system. In 2010, the telescope was approved for what's called the Major Research Experimental Facility Construction Funding, MREFC. This is the fund that funds things like the Polar Explorer ships or things that individual pieces of the National Science Foundation can't afford to build by itself. And so it took 4 years of reviews to get the National Science Foundation and the Department of Energy to allocate the $1 billion that it took to build this thing. Construction started in 2014, so it took 4 years to get all the approvals done, and 10 years to build the thing. COVID didn't help, right? It delayed things a fair bit. But you can see that over the years, things got built. The big mount, which looks very much like the design, was actually built in Spain. This is actually a picture in Spain of the thing assembled. And then they had to disassemble the whole thing and ship it to Chile and reassemble it inside the telescope. So where is it? It's built on Cerro Pachon at 2,700 meters in the sky. It's on the west spur of the telescope. This is not the high Andes. If you imagine, the pictures of the giant glaciers, we're in the foothills of the Andes, but high enough, and it's the first big mountains coming in from the ocean. In fact, if you look on this corner, you can see the city of La Serena where you fly into. Those are those lights. Conveniently, the fog at night tends to block those lights, but on the other side, you can see this shining bit is the ocean. So you can look down on the ocean directly from the observatory. Questions? Exactly.
It's really cool that you can see the ocean from.
Yeah, so one of the favorite activities is to look for the green flash. Many people sitting next to me claim to have seen it, and I have never seen it.
My wife
I
saw
always-
it last cruise.
I always look too soon, and then I have the little green flashes everywhere, but that's green flash.
What do you think the odds are of someone doing a vanity long distance selfie as a promotional thing?
Oh, that's an interesting idea. The neighboring mountain CTAO is actually open to tourists once a week, so you can actually go up and take a picture. I don't know if you can stay to sunset to take a picture. It is a fun place to be. All right, so I said this is an extreme telescope. The outer mirror has an f of 1.18. The tertiary is f of 0.3. And the secondary, which is a 3.5 meter mirror, that's the secondary, is an f1. The total thing is an f1.23 telescope. In other words, it's a telescope almost as wide as it is tall. It's a sort of very different design. And the reason you build this design is that the focal plane is this big. It's 0.6 meters across, and it covers 3.5 degrees in the sky.
What does the F stand for?
So focal ratio, it's a focal length.
Okay.
And so shorter the focal ratio, the wider the field, but also the thinner the focus is. So one of the challenges of this telescope is you have to work very hard to keep it in focus. But it's intended to bring light from about 350 nanometers out to 1.1 microns to the same focus. And it's extremely fast, which is, again, part of the idea of doing a survey. In order to keep it in focus, the cell and the mirror cell, keep in mind, even with the honeycomb, the mirror plus the cell weighs 40,000 pounds, more than and that means you need both the primary and secondary to have active pressure supports that keep the mirrors in exactly the same shape. The secondary is attached to what's called a hexapod, which is a system which allows the secondary to move relative to the primary so as to keep both the distance between the two and the translation as close to possible as to center. So there's a lot of machinery that goes into making this telescope. The mount and the assembly weighs 380 tons, but it has to slew across the sky in less than a minute. And that leads to an interesting problem because the telescope moves faster than anyone can run. So there's a very strict prohibition on anyone being in the dome when the telescope is operational, because you can't get out of the way of the telescope, no matter how much you try. At the same time, it has to settle at a time of 5 seconds, because it has to be able to take the next exposure 5 seconds later after the end of the slew. And that means it has to be extremely well balanced, and it takes a tremendous amount of power on this thing. How many of you have cars with regenerative braking? The telescope has regenerative braking. To get some of the power back whenever you have to stop the telescope. It's a good idea.
John,
Yeah.
when you're stepping through the sky, you're not going from the eastern horizon to the western
So
horizon.
this requirement is basically driven by the gravitational wave, the capability of following up gravitational waves, which we don't know where in the sky they're going to be. Yes, during a general night, if you actually do the simulation of where it's going to be looking at, typically it's going to be moving of order 10 degrees between exposures. But it has to be able to go a minute later and find the gravitational wave afterglow, because there's a need to find out right away whether there's an optical problem. Yeah, no, that's a very good question. It isn't, during regular operation, it's just going to do this. Now keep in mind, the field of view is 4 degrees, so it's hardly ever going to move less than 4 degrees between exposures.
Jan,
Yeah.
who designed this thing?
So it's designed by a bunch of people. I mean, the observatory has had a staff of tens of people working on it, but the original design really is very similar to the design that Roger Angel came up at the Stewart Observatory in Arizona came up. A lot of engineering has gone into making the mount be able to stop and stabilize so fast. The heart of the telescope is the camera. The camera itself costs several $100 million of Department of Energy money, and it was built at SLAC at Stanford. It's actually built in 2023. This is a picture I took when I visited of the camera, and a quiz for you is what filter is in place in front of the camera? Want to guess? Any other guesses?
Sulfur too.
You're seeing the reflected light. So it's a red filter because it reflects all the blue light
Oh.
and the red light goes through. If you show me the red filter, it'll look, the blue filter, it'll look red because it wants to reflect off all the red light and not accept the blue light. The camera, just to give you a sense of scale, is that. This is a picture of the camera actually arriving at the summit last year. Here's a cutaway view showing the lenses. The filters, there are 5 filters in place at any one time. They are stowed at the side of the camera, and then a motor drives the filter in place, again, within 5 seconds. The shutter itself is 1.8 meters across and has to move in less than a second. It is a guillotine. And it's inside a door that keeps the system at a fixed 150 Kelvin. And this is actually one of the things we're still working on. Right now, the temperature excursions are almost a full Kelvin.
Detector of CMOS or CCD?
It's a CCD. It is not one CCD. There are 189 4,000 by 4,000 CCDs covering the full 11.2 square degrees of the sky. Each science CCD is a 4K by 4K and set to read very quickly. It's designed in a system where each CCD is divided into different readout channels. So you can read out the entire 189 CCD or 3.2 gigapixels in 2 seconds.
That image, how it shows the field of view.
Yeah, this is the sense of the field of view. The full moon fits many times in the field of view of LSST. This is why it is such a fast telescope. The CCDs themselves are deep depletion CCDs. They're designed to be extremely red sensitive. When you think of CCDs, the standard picture is like a flat thing with cells, but each of the cells of the CCD is 10 microns, which isn't that dissimilar to the CCDs you can buy in amateur astronomy. However, the CCDs are 200 microns tall. Think of downtown Manhattan and not a flat surface. It's basically a set collection of skyscrapers in the grid. Every CCD cell is much, much taller than it is wide. But it allows you to get to sensitivity of around 90%. So 90% of the photon volume. It's not actually 189 CCDs because at each of the 4 corners, there's an additional 4, typo, CCDs. 2 of them are for guiding. You need to have a guide star to make sure that during the exposure, you're actually pointed to where you are. But the other ones are the most interesting ones. The wavefront sensors are CCDs that are pistoned, one slightly above and one slightly below the focus. And they're read out continuously. So rather than focusing the telescope is designed to keep the central focal plane exactly between the 2 out of focus images so that it will stay always in focus. And this is a technique that's been used now for a couple of large observatories. And I can tell you, it saves us so much time in refocusing over the course of the night.
A narrow depth of field would almost.
You need it, right? Because you can't you'd be refocusing all the time. So interesting enough, I showed you a picture of Vera Rubin. One of the first PR pictures of the camera is actually a picture of Vera Rubin. Well, it's a picture of a photograph of Vera Rubin taken with the 180 CCDs. You can even see the 4K by 4K CCDs, 1/2 out of focus, 1/2 out of focus, up and down at the corners of the field. The guide CCDs aren't doing anything because they're not actually tracking. There's a bit of history behind this. In order to get this picture, of course, you needed light coming in from infinity. So we had to build a camera obscura to take the pictures because this thing wasn't attached to a telescope. And in fact, the very first picture was a picture of someone had bought a head of broccoli. They brought the broccoli and then took a picture of the individual bits of broccoli.
Is it a flat focal plane or curved?
It's nearly completely flat. There is an issue with it in that it is not flat at room temperature because it needs to be flat at 150 Kelvin. And so a lot of engineering work into making the CCDs just the right degree of not flat, so that when you cool them down, they would be flat.
What's 150 Kelvin in Fahrenheit?
Well, let's see. In Celsius, it's minus 107. No, minus 120.
Okay,
So that's like minus 180. It's liquid nitrogen.
all right, so it's cold.
It's cold. And all that is just to make the detectors less noisy and more sensitive. I just have an animation here, due courtesy of John Peterson. So what you're going to see in this picture is the path of photons through to the detector. So let's see if this will play. Hopefully it plays. So on the top left is the sky. That is what's happening in the universe. Then there's the clouds, well, the atmosphere. There's light bouncing off the telescope. So you see light is coming in from space. It's making its way through the atmosphere. It hits the primary mirror, bounces off the primary mirror, off the secondary, off the tertiary, into the camera, goes through the lenses. The lens of the camera, the first lens, L1, is larger than any refracting telescope ever built. It used to be the largest lens ever built, then the DESI experiment built. It's a 1.6 meter refracting telescope, which is just the lens of.
How many elements?
It's a 3-element refractor. So a 3-element lens system. Not sure why this is the set of images it shows.
Now, how do you keep that from warping?
The lenses are held in a cell, and again, the hexapod accounts for any warping as a function of position because it allows the distances and the shifts in the position to change. But the lenses are made out of a very stiff material. Like it's not near, even though it's much bigger than Yerkes, it's a much lighter material because they're meniscus. They're not a solid piece of glass. Okay. So there was a question before the talk started about whether I will get any time on this telescope, and the answer is I will not get any time on this telescope because this telescope will run very different from other telescopes. There are no proposals for this telescope. There are no principal investigators. The data will be the same for everyone. It is a telescope designed to just look at the sky. The data is public after 80 hours, with 2 exceptions. If you care about a very small region, currently 25 pixels by 25 pixels, you can get that right away. That allows the people who are interested in variable objects to get something. There's a lot of debate whether you get enough context that way. The reason this is after 80 hours has to do with our military, because a telescope of this size will see everything that's up there. And they want enough time to reposition what's up there so that the public doesn't see what's up there. Or at least the public doesn't know where it is now. They can tell where it was. But you can get access to it. Anyone in the US has access to this data. It is not proprietary to anyone. Every time the telescope takes 30-second exposures, shifting each time, and coming back to the same position mostly over and over during the 10-year survey. One of the interesting things about the telescope, other than other telescopes, is that the camera is not equatorially mounted. The camera has a rotational axis, and we randomize the rotation in order to sample all the possible rotation. This allows the diffraction spikes not to line on top of each other, so that we really do map the entire sky over the course of the survey. We don't lose light as the way you would if you kept the same orientation of the camera. Again, a lot of thought went in.
Do satellites make a mess of them?
Oh yes, I'll show you a picture of satellites making it. Yeah, that is a problem. So the estimate is that every 42 seconds, the shutter will close a little over 1,000 times a night. And each time the data will be taken. When the data is taken, it doesn't stay in Chile. The data flows through 2 dedicated cables. They were not completely laid out for LSST, but they were laid out with LSST in mind, to Miami. And then from Miami over the backbone of the internet to Stanford, and then to data facilities in the UK and in France, which will process the large portions of the data. And this will happen again every 42 seconds. The idea is that it will take as much time or less time for the image to arrive in Stanford, because the processing of the data will not happen in Chile. Because we're interested in things that change during the night, we have to figure out what has changed in the image before the next image comes down. So we have 42 seconds to figure out what has changed in every exposure. That will result in about 10 million different announcements of things changing each night. And then somebody else will have to figure out which ones are interesting. And there are people working on this problem right now, trying to figure out, okay, you can't possibly look at 10 million things and figure out which changing. Most of them are going to be random variable stars, things that are not as interesting, but figuring out what makes something interesting will be useful. This is the sky survey plan. As you'll notice, it's a telescope in the southern hemisphere. We're not going to look very far into the northern hemisphere. Yep.
In regards to your, what you're talking about with having to see the differences in these images, having 10 million of them, you said?
10 million different, alerts.
Would it be possible to have AI or something like that implemented in order to kind of sift through that data?
Yeah, there are people working on what are called brokers, where you say what sorts of physics things you're interested in, and they will figure out which of the alerts they should pass on to you. Tests have been run with smaller telescopes that seem to suggest this might work, but of course we haven't gotten to the scale of 10 billion things because we don't have anything that can produce 10 billion things each night. Each image, each region of the sky that's in the survey will be visited, at least for the main survey, about 1,000 times over the course of 10 years. So you're building a deeper and deeper exposure. If you won't care about the deep sky, you want the additions. If you care about varying things, you want the subtractions. We'll try to provide both those things. The deep part of the sky, that region of the sky, we visited on our timescale, minute timescales, day and year, and the stack parts will be released about every year. So roughly every year, starting in 2026, you should expect to see the next image of the southern sky deeper each time. That's a little bit of a lie. The current plan is to divide the sky up and go to full depth in smaller patches because some people want the science on the full depth over part of the sky faster. And doing the whole sky this way would lead only to full depth anywhere after 10 years. There are little patches in yellow. These are the few regions that are actually going to be hit much, much more often to get the deepest possible depths. So what is the telescope going to do? Well, there are four main science goals. One I care most about, that I'm most closest attached to, is the study of dark matter and dark energy. We'll use the effect of gravitational lensing to measure the clustering and its evolution, and that tells us something about how dark energy has changed the expansion of the universe. You may have seen the press releases from the DESI survey suggesting that dark energy is time evolving. We'll find out. The second topic we've already talked about has to do with the transient sky. Covering the sky with a big telescope on really short timescales is something that's never been done. If nothing else, because the readout time of the big telescopes tends to be measured in minutes. So anything that the 2-second readout times allows you to find things that have changed in the course of seconds. And we don't know anything about faint things in this region of the sky. There's probably a bunch of stuff there. We know there are gamma ray bursts at the brighter end. We don't really know if there's something below that, though. And there are some hints from relativistic explosions that there are some things out there. The processing, as I said, was divided between the US, France, and UK, and the dedicated cables carried the data. The third science goal, and potentially the thing that allowed us to get Congress to approve this thing, is the census of minor bodies. Now, there is a lot of worry about killer asteroids, and something of this size and speed will discover all of the dangerous near-Earth asteroids, and the main belt asteroids down below kilometer, and all the things in the outer solar system that are big, potentially Planet 9. It's there. And then the last thing is mapping the Milky Way. But if you think about it, anything that you can do with the data, any bit of astrophysics will be done because the data is public. There are already 8 science collaborations that have been formed to study these different areas. They're listed there. And there are about 3,000 scientists in those collaborations that are part of this group looking at this. Well, we'll be looking at the data. There's a much smaller group of people who are working on the commission. There was a question about satellite constellation. This is one of the big challenges. Whenever you build something with a big field, the skies are getting more and more crowded. So this is actually a simulation. We do have pictures with other CCDs, but you notice this is the the array, actually, no, this is MegaCam. This is from CFHT of a satellite constellation passing through it. We are actually working with the makers of satellite constellations to see if we can mitigate the problems. So far, limited success. Each time they do something, and they have been receptive to thoughts of doing stuff, but each time they do it, it doesn't really fix the problem. The problem is that a telescope of this size really is sensitive to everything. And the problem is not so much the pixels that you lose, but that those regions are so saturated that the next exposures are actually have a glow from the residual light. So the afterglow is the hardest part, because this you can tell, oh, I'm not going to use those pixels. But you then need to know what that was in the previous exposure to figure out which pixels to ignore in the next tier. So
Yeah, be seen with the Starlink setup.
Yeah,
so like
this is a Starlink.
of.
Yeah, you know, one of the unfortunate, one of the truths about the world is that there is no legal framework limiting the brightness of satellites and limiting the construction of satellites. There is an international registry. You're supposed to announce that you are launching a satellite. There are currently, I think, 400,000 or 500,000 satellites that people say they will launch. Whether they will launch them or not is unclear. But there's no limitation. Unlike, say, the radio, where there's an international treaty that says you will not produce any radiation in these following wavelength bands, there is nothing like that.
When you see brightness, like, is this the reflected light coming off?
It's
Or is it
sunlight.
just like the?
No, it's sunlight. And the problem is one of the ways to get these things to be fainter is to put them higher up, but then they reflect sunlight for long. So one thought has been to actually make these things really bright, but put them low enough so that only the 2 hours before and after sunset actually get enough reflected light. Because once they're in Earth's shadow, they're not actually reflecting. They're not emitting very much light. So here's the project timeline. The camera went on the telescope on February 1st with one raft, one set of 9 CCDs, and we took a month of data. The full camera was installed at the end of March. Sometime 2 weeks later, they actually exposed it to the sky, and they've been observing every night that's clear. In Chile is about 80% of the time, testing out the system. Right now, one of the jobs I have is I'm looking at scattered light, and turns out one of the downsides of having such a fast system is that light from off-axis happens to bounce off things. There's a feature which appears to be coming off part of the dome aperture, entering the system, and so you get basically a line of light that comes off, a reflection off the edge of the dome aperture. And so we're tracking those things down. There's a baffle that's going to be installed, and the hope is that we'll try to get rid of most of those and then try to paint or try to minimize the reflectivity of everything else.
How do they do flat?
There is a giant flat field, but there's a separate system. There's a laser system that images the flat field with monochromatic light. They can build a flat field by shining successive images at different wavelengths and building up a picture from them. Yeah, it's going to be done through. I don't have a picture of the focal plane of the flat field screen. It's a cool system because it can't be flat, right? Because it's so close together, you have to keep it the same distance with the focal plane. So it's a system that has basically the same picture as the same shape as the effective aperture of the telescope. Anyway, the images are fantastic. They're working very well. I wish I could show. The first light celebration is now June 23rd. You'll notice in this diagram, which was in May, they were saying in July. The plan is to begin operations in October and to actually start the survey with 10 years shortly thereafter. Yeah.
Have you seen any of the pictures?
Yeah. The things they made me sign say that I cannot have anyone look over my shoulder when I display them on the laptop. Any talk I give cannot include any pictures, and I cannot take the physical files away from Stanford. So I have to log into Stanford's computer, view them on Stanford's computer, and leave them there until June 23rd. And then they will release a bunch
Are
later.
you able to talk a little bit about what you've seen?
Yeah, so again, the images are very nice indeed. The image quality, one of the big questions we had was whether you could actually get over the full 3 degrees, the uniform seeing. And that has been delivered. We've gotten a couple of nights where images have gone down to about 0.7 arc seconds. We've also had a couple of nights, we think it has to do with the temperature stability of the camera, where the external monitor, the seeing monitor outside, suggested it should be sub-arc second, but the images were not. So it's not perfect yet every night. But the focal plane focus system, that system with the active measure pressure support really does work. And you can get the image at the right depth. As I said, we still have more scattered light than we'd like. We're still testing out the photometric calibration. So the laser system went on. They during the next bright moon phase, they will take some of the nighttime time, close the telescope, try to get as much light through the flat field system. And that's all part of this commissioning on Sky Engineering, which is supposed to then take us to October. And then they'll do a couple of short surveys, not covering the whole sky, but covering portions of the sky just to see how it will work. And then begin this 10-year process of data. What will be released on June 23rd is the data from the first draft. First draft camera is the small camera, with field of view only about 40 arc minutes. But that also has some cool results. We're also not allowed to write any papers based on the data until after they release it. So we have a couple papers queued up of analysis that's done with a small camera that we will officially start putting on the document system June 23rd.
Can you say what's been imaged?
No. And in fact, I have not seen the press release images, so I don't actually know what they picked, except that the person who's preparing the press release images said, "Oh, they're going to be nice and big things." So you can sort of guess what's nice and big in the southern sky. There's a question, Laura. Do you have a question online?
Yeah, you said that
Sure
June
do. Let's see.
23rd.
Oh, it's Linda. This is
Oh, Linda, sorry.
greetings. Oh, that.
Can we hear it? Oh, no. There's a
Oh,
raised hand.
somebody is speaking.
There's a raised hand, but Laura, I can't hear you.
Well, I stopped because
Let's
someone
see.
else was speaking.
Hold on. We're trying to see if we can get the audio up on our end.
Can you hear me?
Yeah, we might need you to type it in the chat.
I
Okay.
can hear you, Laura.
Yeah, no, I just had the volume down. On the,
Okay.
on the
Can you
laptop.
ask again?
Yes. You said that on June 23rd that astronomy clubs could get a way to see
Yeah.
the first. Can you give us or make sure we get that kind of information so we can do that?
Yeah, Michael has it, and one of the things I'm like 4 slides from the end, but there is a slide about that.
Okay, thank you. That's all I wanted.
Yes. Okay, we're not done. There is a successor to this telescope. It's not built on the ground. It's a NASA telescope. NASA's Roman Space Telescope is one of the few things that has survived the budget cuts. It's finished. It finished its. Those of you remember the James Webb vibration test fiasco. Roman just passed its vibration test. It's all constructed. It's set to launch late next year, early 2027, and it is the next space-based great observatory. Yeah.
How does it compare to the James Webb Telescope?
It is different from the James Webb Telescope in the sense that it is a smaller mirror. The mirror itself is a Hubble mirror, a twin of the Hubble. The spacecraft is designed, the optics are designed to be a much faster telescope in F ratio terms than Hubble. So its camera is designed to have a 0.4 square degree field of view, which is 500 times the field of view of Hubble. The detectors are CCDs, but they're not silicon CCDs. They're mercad telluride CCDs that operate out to 3 microns. So it's red optical to 3 microns. Doesn't go as far into the infrared as James Webb. It's not as big a telescope. It has a field of view of only 200 times bigger than Webb. So it's designed to map the sky and not to go very, very deep on a small region. And so it's still, its field of view is, after all, 1/20th of the LSST's, the Rubin Observatories. But it's in space and it's in the infrared. Its 5-year survey will look at 1/7 of the LSST field and provide the infrared and higher resolution imaging over that 1/7 of the sky. NASA missions, as those of you know, are designed to have a last lifetime of the mission, and they're always designed to last much, much longer. Typically, it's 5 years. Hubble's been up for 35. So we're hoping that they'll eventually map everything, but for success purposes, they have to say, no, we have to live for 5 years. And so that's the time of the mission. This one will have principal investigator surveys, so I'm hooking up ideas for things I'll propose for this telescope today. So I can't show you pictures from LSST, but luckily next door on Cerro Tololo, I do have a camera. It's only 2 square degrees, but I did expose on it for long enough that this is about the depth of image that you're going to get across the entire sky with LSST, except this is 100,000th of the sky. Wow. So this is a little bit less than the full moon. There's about 400,000 galaxies in this picture, just to give you a sense of what's going to be there. And this is the kind of images that will be released in 2030. So we should have a watch party. The conclusion. All right.
What part of the sky is that?
This is Abell 3667. It's about deck of minus 30 something, so it's not a great target from Seagrave. But it's a merging pair of galaxies. You see the 2 giant ellipticals. It's got some interesting spiral galaxies in it. I just picked it because we just wrote a paper. All right.
Is it more critical to keep the Rubin clear of dust and dirt on the mirrors than it is on the otherwise also?
Not so much in the sense that it will degrade. One of the things that the reason the building is built that way is that under the telescope, there's an illuminizing cell that's 8.4 meters across. So you just lower the mirror down, re-illuminize, and lift it back up. And it's designed to do that every, I think, 9 months. Yeah, actually, can I turn on the light?
Yes.
Good. See. Oh, sorry. Right, like, question and then Steve.
When we were in New Mexico at just outside of Socorro, I'm having a brain fart.
Las Cruces.
No, just outside of Socorro.
Oh, it's a very large array.
Jimmy, what was the observatory? We visited.
Up on the mountain. Yeah.
Oh,
Magdalena Ridge.
Yeah.
Magdalena Ridge. That primary is a Hubble primary.
Yeah.
And I asked him, because they don't have an illuminizing tank there. And he said, well, the coating on this is the same coating they use on the Hubble. So it's good for about 30 years.
Yeah, it's not.
Is that similar?
No, this is not. And it is true that the coating on the Hubble is good for 30 years in a space environment.
Yeah.
I'll bet you the Magdalena Ridge telescopes lost some reflectivity over the years because inside the atmosphere is a bunch of oxidizing stuff. Absolutely not. And aluminum does this. But yeah, it's that telescope. This telescope is designed to be reused. They actually built the luminizing tape.
How often would they have to do it?
Their plan is to do every 9 months. I don't know if they actually need to, but again, they've got the cranes. It's right underneath the primaries. They just have to lower the thing down, re-illuminize, raise it up. It is 30,000 pounds to lower and raise, but they've got the cranes.
So is that a couple days of downtime?
Yeah, they'll probably do that during the winter shutdown. This January is not the most July is not the most wonderful month.
Now, what about
They're
the
ready.
secondary there? Is that?
A good question. I don't think the secondary is supposed to be illuminized as often. It is pointed upside down most of the time. So it's not picking up nearly as much dust. But yeah.
What does that mean? Re-illuminate?
So the mirrors are glass, but in order to enhance the reflectivity, they coat it in a metal, a very thin layer of metal. And that layer is so thin that it's not particularly durable. And so what they do is they chemically etch it, they put it in a tank, chemically etch it, and then re-vapor deposit a new very thin layer. And the fresh aluminum has a higher reflectivity that increases your sensitivity. You put it up. Yeah.
In one of your early slides, you had a picture of what the field, not the field of view, but
Yeah.
the southern sky basically, and everything, yellow kind of circles or ovals. And you said they were gonna go, it was gonna look deeper into those areas.
Yeah,
What's in those areas?
So the deep drilling fields are a combination of places where the Euclid satellite is looking and other people, like the X-ray Chandra satellite has had a deep field where they've stared for a few million seconds in an area. So the idea is regions where there is more data. There's one field that Hubble's a tiny field view, but they did build one field called the Cosmos field where they stitched together to make a 1 square degree field. That's one of the deep drilling. And the plan is to visit those roughly 10 times as often, so that in the first year they reach the full year depth. And they'll just keep doing it every time.
So they're not the Magellanic Cloud.
They are definitely not the Magellanic. No, the Magellanic Clouds are difficult because saturation on this thing is 17th magnitude, and there are stars in the Magellanic Clouds that will saturate the dust.
Wow. What happens with a bright star like Vega? That's just a field. It's not a
Well, so the scattered light stuff is amazing. You get rings all over the place because there are so many. Like there's 3 lenses, right? Every lens has a very small reflectivity. That light goes back to the primary, to the tertiary, and comes back in to get another ring. And so we have a software that's designed to monitor these things. Yeah, so the plan is to model and subtract the optical path. So once you know how bright the star is, you can actually estimate and make an attempt at subtracting off all the scattered light. You'll see how well. That's still in progress.
How far back are we gonna be able to look?
So far back is a difficult question because the telescope naturally sees brightness. So something that's very bright can be seen incredibly far. So the optical afterglows of gamma ray bursts will be able to be seen up until the redshift where the near ultraviolet, basically the hydrogen absorption cuts off. So it's not a sensitivity issue, it's that the space between us absorbs all that light.
Right.
The reason Webb can see further is that it looks in the infrared, which means the redshifting allows it to go to find the redshift 20. Here, our limit is 1.2 microns, and that's redshift 9.
You're not gonna
or
see
so.
as far back. with
Yeah,
the scope
so
as
beyond
you see
redshift
it.
9, you won't see anything because the hydrogen in the way will absorb it. Redshift 9 is a lot.
Yeah.
Bob,
You say this is the dark matter telescope originally?
that's what we proposed it actually originally to Microsoft and then to the NSF as the dark matter telescope, and then it changed names at least 4 different times before becoming the Vera Rubin.
Well, I read certain articles today about the dark matter issue and whether it's a real function of gravity, and that there may be other particles, muons, or type of Higgs particles that somehow modulate the strength of gravity in different areas. Lots of different ideas now about
There are.
the constant value of gravity.
Yeah, people have looked at this. It is, I will say that the solutions that work for one part of it so far have not been widely out. The reason, and dark matter is an uncomfortable thing, right? Something we can't actually measure only gravitationally. No one really loves. The alternatives turn out not to work so well. Like changing gravity doesn't work on the right scale. So there's a very popular theory called MOND, which works very well on galaxy scales. But fantastic job. Doesn't work on larger scales very well. It doesn't work on the radio signal. No one's quite yet figured out a way to make it work. Doesn't mean people aren't trying. So people are still going to try. We don't have a better alternative to dark matter. Basically,
There's
right.
another whole science like quantum mechanics is for the real small stuff. Maybe there's a set of rules for extremely large.
The problem is that certain very large things seem to behave exactly the way the rest of physics appears, and just other things don't. And so you can't change the laws. You have to change them in a much more changeable way, and that's really hard because the minute you start saying that the laws of physics are different everywhere, then all your predictive power goes out the window. So we're not going to go there until we really have to.
We got another question from the folks on Zoom.
Sure.
Laura?
Go ahead.
Yeah, I'm interested in the frequencies with which you'll be imaging. You said you had 5 filters, and what are they? And what wavelengths will you be imaging in?
So it turns out the survey will be done in 6 filters. There are only 5 that can actually fit on the telescope at any one time, and we have to keep swapping them out. Swapping them, it takes about 2 hours, so it won't be done during the night, they'll be done between nights. The filters range from, they're the filters originally designed by the Sloan survey, they're U, G, R, I, Z, and Y. U is ultraviolet, it's slightly bluer than our eyes can see. G is blue-green, R is red, I is near infrared, and then we ran out of letters. And so Z is slightly more infrared than red than I, and Y is even more infrared than Z. Basically out to the detector limit of silicon. Silicon CCDs work by the photoelectric effect. There's a band gap that limits your energy. By making these towers, we've actually squeezed a little bit more at the cost of a bit of efficiency, so we can get down to about 1.1 microns.
Okay.
So it's between 350 nanometers and 1100 nanometers, or 3500 and 11,000. Thanks.
Okay.
So near ultraviolet to near infrared. And the plan is whenever the moon is not up, the 5 filters installed will not include the most red filter. And whenever the moon is up, the ultraviolet filter will be off, and we'll replace it with the reddest filter. Because the moon, it makes the sky so much brighter in the ultraviolet.
And how quickly can the filters swap out?
It's a couple of hours. It'll be done during the day. It won't be done during.
No, I mean,
The filter wheel is designed to swap filters. I think it's 10 seconds.
10 seconds. Yeah, that's
I
pretty.
don't know. It's got to be less than. I actually saw it in Stanford, and it was like a boom, boom. So 5 seconds to shift the filter. It's moving a 1.5 meter filter across a 1 meter filter.
There's a video of it online somewhere.
Yeah,
And you can dampen vibrations from that, I suppose.
Yeah, you don't want to be exposing while that's happening. But again, it's supposed to damp. The claim is, and so far it seems to be true, that it'll damp within the 5 seconds that it takes the telescope to also stop vibrating.
Yeah. Okay.
So the exposure will be 30 seconds, but roughly the mean time between exposures is 40 something seconds. So you get a sort of 10-second slew and settle time, in which things like filter changes will occur.
That's pretty cool.
Yeah. Question. You had a question.
Yeah, you mentioned that on average, any individual point is going to get about 1,000 visits over the course of the survey. What's particularly uninteresting about some of these strips that stay in the purple in the middle? Or
Okay,
are
so
they so crowded.
So the purple in this projection is the ecliptic plane. And so the sky is brighter. I'm sorry, it's the Milky Way. And so you don't want.
There's just no sense. Yeah.
You don't want to look too far into the Milky Way because you get too much dust absorption. The north ecliptic spur is a little awkward for the telescope to reach. The telescope has to be tilted a fair bit over, and so it's less efficient to observe there. And so by design, they're not going to go as deep in the north ecliptic sky, even though you're away from the Milky Way and the skies are dark. The telescope was in the north. There was a site selection for the telescope. There was a site in Mexico where it was a northern hemisphere potential site. It didn't get picked, so we won't get anything north of that. And now Roman's plan is also to image where LSST is imaged. So Roman, currently its survey will also not see the northern sky. But people can propose to look at the northern sky with that. Other questions?
Is there a specific pattern of the imaging, like will it stay on the meridian and then just when the
Yeah, so it's basically designed. I think there was a question about not wanting to shift across the sky. Steve, you'd ask that question. There is a simulator and there's a nightly scheduler that figures out where it's looked at and figures out what is the most efficient from a slewing point of view mapping. So actually, most of the time when you look at it, it's slightly to the west of the meridian. You end up chasing a little bit. So you're not actually looking right at the meridian in terms of efficiency. I wouldn't have thought it that way, but when you run the scheduler, that's what it does. So you're always sort of half hour to an hour west of meridian. Yeah.
Geography and climate aside, where would be the ideal place to build a ground-based telescope to get the best broad view of the sky?
I can give you 2 locations. One is another 4,000 meters up or 3,000 meters up in the Andes. So there are several fantastic sites at 5,500 meters. Hard to build. The high domes of Antarctica, not at South Pole, but a bit further south, they're also at about 3,000 meters or 4,000 meters. It's 4,000 meters of ice, not rock, but still. Those have fantastic image quality because the katabatic winds come from there. So they give you extremely still hours. Unfortunately, they also give you minus 100 Fahrenheit temperatures. So you don't really want to build the telescope, or people have been thinking about building telescopes. Those are the best places in the world. The third best place, bringing power from the coast to those places is really the big thing.
That would be the challenge.
The third place is Mauna Kea, which on the surface of the Earth is one of the best places. It's again, it's in the middle of the ocean, so there's nothing to make the air turbulent for thousands of miles. The tallest thing, so you hit Asia, and so it is a great place to be. People want to build telescopes there. There are solutions.
Any other questions for Jan?